Hi, Purvi. Good evening.
Am I audible?
Yes, you are audible.
Good evening. Can I ask one question, Dr. Purvi?
Yes, please go ahead.
Yeah, yesterday you were talking about the high and low pressure or flux circulation regarding this one. Both the terminology in the 2D and 3D will be same meaning.
Yes. So if when I'm talking about, if I write F dot N, that refers to flux, both in 2D and 3D. And if I write F dot T, that refers to circulation. Again, doesn't matter whether the curve is in 2-dimension or 3-dimension.
But the sense of high and low will be same sense, either 2D or 3D.
Yeah. So it was not used in a technical sense. What it meant was that when you evaluate, you expect the flux to be a larger quantity than when you evaluate in the second setting. So that's all it meant.
And always be in the direction of normal, that will be low, and other
right. So if you're so let's say that you are interested in the outflux, and then you're taking your normal outer normal, then in that so suppose the direction of the flow is along the normal of the surface, then you expect the outflux to be higher.
Yeah, and opposite direction, that will be low.
Yeah, so in that case, there is no outflux, right?
Yeah, influx.
So you'll get a negative quantity between minus. Yeah, exactly. So it will be so the plus minus will indicate the sign. But when but if I ignore the sign, then sort of zero, if I got a zero quantity, that indicates that sort of my flow is tangential to the surface. That is why I'm almost getting no flux. You know, if the flow is tangential to the surface, then its inner product with the normal will give you zero.
Yeah. Regular means continuously differentiable, right? Means or something else?
No, so when I use the word regular, it refers to the map and it means continuously differentiable, and I want that the derivative is non-zero everywhere. So it's more than just continuously.
Like complex number, when we talk about the regular, the similar meaning is that.
Yeah, for a so there are different usages, I agree, but when I'm talking about curves, regular comes with this additional condition that I should have a non-zero tangent vector everywhere.
Okay.
Right, so let me share my screen in the meantime, and then maybe we can start with actually questions if people have questions. So yeah, so good evening, everyone. I hope my screen is visible.
Yes.
Excellent. Yeah. So maybe before we get going, I mean, we will continue on this theme today. Also, we will be spending time on. In fact, we will be spending time in the 2 space today. So we are not going to go into 3 dimensions today. Tomorrow's lectures will be about surfaces. So we'll be spending more time in 3 dimension, both the lectures tomorrow. But maybe before we get started, if there are any questions about what we discussed yesterday, any clarifications on the notation, they're most welcome. Otherwise, I'll get going.
I have a question regarding the regular parameterization that you asked for a circle. See, I'm trying to visualize the something. Whenever we say that is regular, then say suppose we are tracing a curve, and maybe the t is, if you look at t as a parameter, time parameter, then whenever it is not regular, means it either changes the direction or it changes the speed, or in some sense it stops somewhere and then either traces in the opposite direction or in the continuing direction. But that is not going to happen for circle anyway, except for the point at which it starts. Whenever you start a point, at that point it would be initially it would be 0. So except at that point, there is no possibility of either changing the speed or changing the direction when it comes to circle, right?
No, so you can construct, so you can construct a C1 smooth map. So I'll actually do it with my pen, in that I start tracing the circle and then I just stop for some time. So I slowly speed down. So I sort of like press on the brake. So it's all happening in a smooth fashion. I slowly step on the brake and I come to a pause, and then I slowly start accelerating again. So when I come to a pause, my gamma prime itself over there could be a 0 for those values of t. So what is happening is I am starting at time t0, let's say at pi or something, I sort of start at a normal speed. Then I slow down, my particle is slowing down. At that point of time, gamma prime will come to a stop, so it will become 0. And then I start again smoothly and pick up speed. So it will still be tracing a circle, but the way I'm tracing it, the speed of that determines gamma prime. So it is completely possible in the middle to stop. Okay, so that's why we have to keep the image of the curve and the function of the curve a little separate. The function of the curve has exactly the interpretation you mentioned, that you think of it as a particle that is traveling and the speed is gamma prime. And at any point of time, you can come to a smooth stop. There's a way to come to a stop. And of course, there are jerky stops and they will not give you a smooth function. They will only give you a continuous function. But it is possible. So if you've seen graphs of functions like this, so they come to a 0 in a smooth way, right? So as opposed to coming to a 0 sharply like this, I'm thinking more of coming to a 0 in a smooth way like this. So this is absolutely possible.
Okay. But in the example that somebody has given, I think Sushoban gave, in that it is only the initial point, not somewhere in the middle of the.
Right? Exactly. So that example, one can even try to, you're completely right there, it's in the beginning. But if you, but you can try to see if that example itself can be modified to put that stop somewhere in the middle.
Okay. Yeah. Okay.
So think about that. Yeah, that's a good question. Yeah. Okay. All right. So let me get started and we can always revisit some of these ideas. So very briefly, where did we end? We ended with what I call the gradient theorem. And what that said is that if you have a curve, gamma, and if you have a vector field which is coming as the gradient of a function, so it's a very special vector field, and it is defined on some region containing this curve gamma, then when you compute the integral of that vector field along gamma, then what you get at the end of the day is just a phi computed at the final endpoint minus phi computed at the initial endpoint. So the actual path plays no role in the computation of this integral. And we also gave this an interpretation because when you do integrate a vector field along a curve, that amounts to the work done in the force field that is created by that capital F. So anyway, we kind of want to move on from there. So, okay, one particular implication of this is that if gamma were to be a closed curve, then of course the right-hand side would be 0. So that means if my vector field is a gradient of a function, then along every closed curve, wherever that vector field is defined, the integral turns out to be 0. Now, this is great if we already know that capital F is the gradient of phi. sometimes it is actually hard to, even when it is hard to recognize it as the gradient of phi, because you can have a very complicated example. And secondly, what if it's not? Then do we have some other ways of computing this integral, right? This is very simple, but I might want other ways of computing this integral. So I thought I'll start with examples of these computations. This will also sort of test if we understood the definition of integration or not. And it'll also be a way to revisit some of the notation we introduced. So I want us to compute. So I have a little picture of this vector field. I want us to compute this particular integral. Of course, I have chosen this integral for a certain reason. And for the moment, we want to forget all the theorems we are going to talk about. So we want to do this from scratch. We want to do it from the definition. And what are the curves I want to use? So let's use the three curves that we saw last time, the circle, the asteroid, and the square. And we'll parameterize it according to the parameterization that I gave for those three examples. Of course, we will not be able to do all three. That is a lot of work. So in the interest of time, let's just first discuss this integral a little bit. So first of all, I want you to recognize this integral. So let us note that capital I is, at the end of the day, the integral of a vector field along this curve, where what is my vector field? What is my vector field hidden over here? So f of x comma y, in the first coordinate, it's 2x square y plus y cube divided by square root of x square plus y square, comma 2y square x plus x cube divided by square root of x square plus y square. And of course, here we are implicitly assuming that we are not on the origin, because there this vector field is not well defined. But all the three curves that we considered, none of them pass through the origin. So there's no problem in trying to integrate this over those three curves. Okay, the second thing I want to mention over here is this notation of dx dy. So this is a non-rigorous treatment, but it's very, very useful. So so this is a non-rigorous treatment of differential forms. So these dx, dy, these are what are known as differential forms. I don't want to go into the theory of differential forms, but here is the reason why we sometimes write it in this notation. So on the curve gamma, so on the image rather, what is happening is that I'm viewing x as the first component gamma 1 of t and y is gamma 2 of t. So technically x and y are becoming functions of this time. So today this thing of t being time came up, right? So that means I can talk about dx by dt. If I view these as functions, I get gamma 1 prime t and dy by dt becomes, dt becomes gamma 2 prime of t. And then we do this kind of fishy business, which is that we say, okay, we can take dt to the other side. And so dx becomes gamma 1 prime dt and dy becomes gamma 2 prime t dt. Now, this is the part where I will put quotation marks, because this is a sort of just a formal way of doing things. But at least in our situation, it works. We can take this for granted. So when I write down this integral in terms of gamma, I translate everything in terms of this parameter t. So now I can write everything. So we'll write down what this AB is later, but what am I getting? So my first component, so I get 2 gamma 1 square, gamma 2 plus gamma 2 cube. I'm getting this. I then have a gamma 1 prime t plus I have 2 gamma 2 square. So they all have this argument t, okay? I'm just for the sake of notation, not putting this t in. Let me write it here. And then gamma 2 prime t. All of this divided by square root of gamma 1 square plus gamma 2 square. And all of this dt. So this just becomes a familiar integral on an interval, right? So now there is nothing weird happening over here. We know how to do these kind of things. Okay, so now we need to take these specific curves and plug in what gamma 1, gamma 2 is. So let's do the first case. The first case is where gamma of t is actually equal to cos t sin t, and t is from 0 to 2 pi. So then what happens is my capital I, so let me plug this all in, 0 to 2 pi. And please, I often tend to make lots of small mistakes. So please make sure that I'm writing the correct thing. So I'll get 2 cos square t sine t plus sine cube t, and then the derivative of gamma 1. So that gives me a minus sine t plus, and here I have 2 sine square t cos t plus cos cube t, and here the derivative gives me a cos t, and everything. Now the denominator is very convenient because gamma 1, so cos square plus sine square is equal to 1. So I actually don't need a denominator. And then there is a dt over here for which I'll create some space. Okay, dt. Okay, so let us simplify this to whatever extent we can. So let me see what all I can take maybe common. So in the first expression, in the first term, I'll just pull out a sign, another sign. So I'll get sine square t. And then inside I get 2 cos square plus sine square. So what is that? That actually becomes cos square t plus 1. And then in this, sorry. And then the second term is plus cos square t. And here I will get sine square t plus 1. Okay, and all of this dt. So don't worry, we are almost done. And finally, so what does all of this give us? So if I multiply all of this out, I will at the end of the day just get a cos square t minus sine square t. And it's almost magical that we are getting something that we actually can write in a very simple fashion. And this we know is sine 2t over 2, 0 to 2 pi, which is a 0. Okay, so a rather complicated integral has turned out to be 0, which is fine. But you should also appreciate the fact that so many things have cancelled and become simple over here. Okay, by the way, if there is any question about this computation, this is a good time to pause before we move to the second example. Okay, so now sort of things are going to get harder because we are going to now try to plug in the asteroid into this equation. So let me just copy and paste this object here because I'm definitely going to forget what this is. Okay, so what happens with the asteroid? So let's at least try to write the expression. Okay, I'm not going to torture all of us by actually trying to compute it. So for the asteroid, remember that gamma t was cos cube t, sine cube t, and t was again coming from 0 to 2 pi. So I will just write out the entire expression. So I get 0 to 2 pi, and let's see how far we can take this. So I have 2 cos 6t, then I have sine cube t plus sine 9t, and then the derivative of gamma 1, which is 3 cos square t, and there's a minus in front, sine t. And then the whole thing I have to do all over again, but sort of in the opposite way. So sine 6t cos cube t plus cos to the power 9t, and then 3 sine square t cos t. And this time the denominator is not as nice. So we get square root of cos to the 6t plus sine to the 6t and dt. Okay, so of course, if somebody gave you this integral, you would not want to compute it, but you say, okay, fine, maybe there is a way to think about this. You try to get all the like terms together. And even though I'm not going to try and compute this by hand, ultimately, what will happen is that you can use some sort of symmetry argument. So there are 4 pieces over here. I'm sort of integrating. So remember, I have a direction to this curve, which makes a big difference. And I have these 4 pieces. So think of these as 4 integrals over these 4 pieces. And I will leave this as a big question mark if you want to think about this from scratch. So my claim is that you can use some sort of symmetry argument to actually realize that this is also 0. So, okay, fine. We are using something here, which is just how well these trigonometric functions behave. And maybe there is some cancellation about these curves. So some kind of symmetry could be that the behavior along this curve is the same as the behavior along this curve, but it comes with a minus sign. So you can use these various rules. And let me say about part 3, a similar argument works for the square. And I'll leave you to work with the parametrization. But what is the point of these three examples? The point is that, okay, fine, we could use some symmetry, but what if now, what if I either, so what if I spoil the symmetry. So instead of saying asteroid or square, I work with some sort of combination. So so some portion of this is the circle. Let's say some portion is the circle, some portion is the asteroid, and then some portion is the rest of the square or something like that. So I mean, my curve is just not as nice, basically. Or the second thing is I work with those curves themselves, but what if I am interested in computing these integrals for the portion of the curve that's in the first quadrant. In the first quadrant. So what I mean by that is I'm not really interested in computing this integral along the full asteroid. I really only want this piece over here. I want to do this integral only, let me use a different color, only along this blue piece in this direction. So then this symmetry kind of argument is not going to help because these cancellations will not occur. Okay, so by the way, so for the circle, this is not a problem because, why is that? Because I'm really just doing the same integral, but from 0 to pi over 2. And for us, we got a very simple form over here. This is what we had. And in the end, this was sine 2t over 2 from 0 to pi over 2. And this will still give you a 0. So for the circle, this is not an issue. But now if you start doing this with the asteroid or the square, you're going to have to deal with an integral like this from 0 to pi over 2. And who knows what that is going to compute to if you try to do this by hand. Okay, so what I'm going to talk about now is going to make life a little bit simpler for us, but let me pause and see if there are any questions at this stage. Okay, so what is the general strategy over here? So basically we are going to be able to use something like Green's theorem. That's going to help us a lot. But where is this idea coming from? The idea is coming from the following thing that let's say, so let's look at these curves. Let's look at them on a single axis. So I have the circle. Then I have the asteroid, the piece of the asteroid. And then I also have the, let's take dark blue. I also have the square. And let me just say that these are all surrounded, like, so they are sort of in some region away from the origin. And if I were able to write my capital F as the gradient of phi, let's for the moment assume that's possible, then what I could do is, so remember I already know that the integral along the circle is 0. That's great. And I want to now know the integral along the asteroid. So I want to know the integral along this curve. So let me call this curve gamma, and let me call the pink curve circle, sigma. And so then what I can do is I can construct this new curve, capital gamma, which is what? It is sigma, and then I take gamma, but in the opposite direction. So I sort of go along sigma, and then I concatenate gamma in the opposite direction. So now, because this is a closed loop, what will happen is that along capital gamma, f dot ds will become 0. So f dot ds along sigma will become f dot ds along gamma. And we have already computed what is happening for the circle. So we then immediately get that even for the asteroid, it's 0. And it really doesn't matter what the shape of the curve is. I could have taken a very complicated curve with a very complicated parametrization. And I would immediately know by the fact that I can compute it on the circle and this important fact that I'm assuming over here, I would immediately know any other curve like this, which is joining the two endpoints of the circle. I would know what this integral is over that yellow piece, and without any need for parametrization at all. But of course, as I said, that this is in general quite hard to know whether capital F is the gradient of phi or not. You try to you kind of have to try and integrate. So how do you figure out, how do you compute an antiderivative? You try to integrate. And what is easier than integration? Of course, differentiation. So instead of trying to do this, we can directly try to use what is known as Green's theorem. So let me write down Green in a sort of general fashion. Let me just write down a statement in as general a fashion as possible. So let E be a region in R2. So this is a result in the plane whose boundary is a finite union of disjoint and now simple closed piecewise C1 smooth curves. And because I'm going to do integration along these curves, I need to tell you how they are oriented. So oriented in such a way that when walking along the curve, in the direction of orientation, E is to the left. And we'll draw a picture. So this is a way of specifying. It might feel a little not fully rigorous, but it does serve the purpose in most cases that we care about. Okay, so this is actually our setup. Okay, so let's draw a picture before we complete this statement. So we have some region, and there are finitely many boundary curves. And when I walk along this outer boundary, my region should always be to the left of me. So when I'm walking in this direction, but when I do this inside, this is what I get. I get these clockwise directions for the inside curves. So this is my E. Okay, now let hang on. So my tablet is giving me a little bit of trouble. So let me. All right. Yeah. Okay. Fine. Give me a moment. Yeah. Okay. So let F from E to R2 be a C1 smooth vector field. With capital F equal to P comma Q. So those are my components of capital F. Then if I look at the integral of F dot P ds along the boundary, and what is this? This is P dx plus Q dy along BE. Then this can also be computed as a double integral over the inside of the region. And I have to take the double integral of del Q by del Y minus del P by del X against dx dy. Okay, and again, dx dy, I'm sort of assuming that we all understand double integration for good regions. That is the assumption. So we are not going to, I'm not going to have a detailed discussion of double integration. But if you've seen Riemann integration for on intervals, then the philosophy of double integration is very similar, that you divide your region into rectangles. You first define what it means to integrate over a rectangle, and then you approximate your region by smaller and smaller, by the union of smaller and smaller rectangles. So in principle, it is very similar to how Riemann integration works in one dimension. But for now, I'll assume that we kind of all know how to do double integration. Okay.
Ma'am.
Yes. Yes.
Yeah.
Please.
It should be del Q upon del X minus del P upon del X.
Sorry. Yeah. Thank you. The formula is important over here. Otherwise, we don't get what we want. Yes. So you differentiate the second component. And of course, we'll understand the meaning of where this is coming actually next time. So when we look at Gauss and Stokes theorem, then the meaning of where this is coming from will become more clear. And I'll keep that for next time. But yes, so this is the correct formula. And so let's just like momentarily pause over here and just, what is the advantage of having a formula like this? So both the directions over here are important. So the way we have discussed this entire thing is that, oh, I actually want to integrate things along curves, and I'm finding a way to transfer this information to regions. But the other direction is also sometimes useful. Sometimes you want to compute something on a region and you transfer that information to the boundary curve. So it's really a very flexible situation. And really, when you apply it, you have to be clever about recognizing which side of the equation you really want to use. So that really is about practice and doing this enough number of times. Okay, so before we come to the proof, I mean, let's just discuss a few. By the way, let me pause and see if there are any clarifications on the statement or what is being claimed over here. Okay, if not, so let's talk about some applications over here, and then we will come to the idea of the proof. So the first one is 2-hour setting. So recall that in our example, what was capital F? So my capital F was this vector field, which 2x square y plus y cube divided by square root of x square plus y square, comma 2y square x plus x cube divided by square root of x square plus y square. So this is going to be my p comma q. And what I asked you to compute is precisely the left-hand side. So what I'll do is, again, I have my asteroid, piece of my asteroid, and then I have my circle over here. So my region that I'm considering, and let's think of this as the axis. So the region I'm considering is between the asteroid and the circle. That is my capital E. So I'm going to transfer this into a double integral over that, because I already know that along one piece of this boundary, this left-hand side is 0. But when you compute, so let me compute del q by del x. So this we have to do using the quotient rule, and I'm sure everybody is very good at differentiation over here, but let's just go ahead and do this. 3x squared minus, so now I have 2y squared x plus x cube. And what is this derivative over here? I get x over square root of x squared plus y squared, and all of this gets divided by x squared plus y squared. So if we simplify this a bit, so I'll take common denominator and I will throw that denominator. So I'll get 2y squared x squared minus x to the 4. Hopefully this is all correct. And I get x squared plus y squared to the power 3 over 2. Okay. And let's just simplify this. So I'll get 2x squared y squared plus 2y to the 4 plus 3x to the 4 plus 3x squared y squared. Is that right? Minus 2x squared y squared minus x to the 4. And then I have this denominator x squared plus y squared 3 over 2. Okay, so some things cancel, thankfully. I get this cancels. And at the end of the day, what I'm getting is 2x to the 4 plus 3x squared y squared plus 2y to the 4 divided by x squared plus y squared to the power 3 over 2. Okay, so good. We were able to do that. Now my claim is that this is exactly del p by del y. Can you immediately, oh, sorry, it scrolled up. Okay, so can you immediately tell me why do I not have to bother to compute del p by del y? So I kind of, I mean, it's a silly trick, but it's still, it saves you some time. Why can I say that this is already the partial derivative of p with respect to y?
Symmetry in x and y. This.
Yeah, exactly. So if you look at the expression for p, the x and y have just inverted their roles. And when I differentiate q with respect to x, I'm getting something symmetric in x and y. So now if the same expression, I change the roles of x and y and differentiate with respect to y, yeah, exactly, role of x and y interchanges. So if you can always save some time by being a little careful about what you're doing. And now what we know is, thus, the integral over E of del Q del X minus del P del Y this area integral is simply a big fat zero. So if I take my asteroid to be gamma, this was sigma, I know that P dx plus Q dy would have been a zero to begin with. So I'm taking only a portion of the asteroid. And as I said, here you don't have to try and recognize whether capital F is truly the gradient of some function phi or not. You actually have to do a derivative. You have to take derivatives, which is actually easier than doing integration. And you can do the same logic for the square or any other curve over here. One thing to be careful about over here is that my vector field, it is not defined at the origin. Okay. And so it's always very important that we be careful about the conditions on our theorem. So the condition is that this vector field that I'm taking, it really needs to be defined on the full region. Okay, so it cannot be that if I'm trying to integrate it over a region, then I have some sort of singularity over here. So if I was trying to apply this story to some curve that went around the origin, then I could not have applied this logic. Okay, I could not have said that why don't we take this entire region to be E, because the problem is then with the vector field. It is not a C1 smooth vector field throughout. And this is not some problem in our ability to prove such a theorem. This theorem will just not be true if you have some sort of singularity over there. So you can construct examples where the vector field has some problem at the origin, and you will not be able to get a green function for that kind of a vector field. Okay. All right. So let's pause here and then maybe move on to the next application. Let's see if there are any questions.
This we can connect with the exact differential.
Correct. So let's talk about that, since you have raised that, and it will also come up in your tutorial. So there are a few things that are being said over here. Actually, there are actually three things. So you mentioned this word exact, but what color should I use? Let me use pink over here. Okay. Yeah. So there are three things. I'm saying F is gradient of phi. Okay. This is that the vector field is conservative. This is also the same thing as saying that the vector field is exact. When you can write it as a gradient of phi, it means that it's exact, but in the physics language, it's called conservative. Okay. So here what one is saying is that, yeah, now if you integrate this along a curve, as long as the curve lies wherever F is defined, you will get zero. But the second thing I'm saying is a little bit different. So if I write F as P comma Q, the second thing that we just notice is that del Py is equal to del Qy. This is the same thing as saying that F is closed. And Green's theorem is saying that if this is true, so if you notice my gradient theorem said that this vanishing will happen as soon as capital F is a conservative field. So as soon as you have this statement, I will have a vanishing. But there it doesn't matter if there is a hole in the center. So if my curve, so let's say my vector field has a singularity, but my curve goes around it, and my vector field is well defined on this entire curve. So let's say it's defined on this yellow region around the curve. This is where the vector field is defined. If it is coming as a gradient, it has to become zero. But Green's theorem is saying that, let's say we don't know whether it's coming as a gradient, but we know this thing about it. Oh, I'm sorry. I keep making the same mistake, which is here it's with respect to X. So this is this different condition of being closed. And what I am saying is, in this situation, to say that you have a zero, this condition, it is not enough for it to hold only on this yellow region. If you want to go from this condition and say that this integral is zero, if you want this implication, this is going to come from Green's. But in that case, this condition really has to hold, at least the way Green's theorem is, there should be no holes where this is happening. Whereas in the above one, it doesn't really matter. It's completely fine. So in general, the question is, when is a closed vector field an exact vector field? That is an important question to which we do know the answer, but the answer is a bit more complicated, and you will explore this in your tutorial on multivariable calculus. So when is a closed field an exact field? And so what we have just seen an example of, this capital F, it is a closed field, okay, by what we have just proved. But is it exact? We haven't shown that. Because I designed this example, I know it is exact because I actually cooked it up by taking a function phi and then taking its gradient. But if I directly gave you F, it would take you some effort to know whether it is exact or not. But closed, we have checked. So I guess this is what you were referring to, and this is what's going on over here. Questions or comments on this discussion? Okay, so what is it that we wanted to discuss? So a few more applications, and then I want to make sure that I get a little bit of time to discuss the proof as well. So the first one was basically to transfer one well understood integral to another integral that we don't understand that well. Another simple example is that you want to compute a line integral, but it's too much of a pain to parameterize the actual line. So I can give you even a simple example. So let the region be 0, 2 cross 1, 3. So it's a square. And even though we do know how to parameterize a square, it takes a little time to parameterize each piece. And I want to compute the integral over the boundary of this square, and I'm always orienting it counterclockwise for this discussion. And I want to compute again an integration of a vector field along this curve. This is what I want to compute. Okay. So again, remember that even though we are using this notation, this is f dot p integrated along B. And rather than parameterizing the curve, I will apply Green's theorem. And why I can apply it? Because if you look at this vector field, it's well defined everywhere and it's C1, it's smooth everywhere. So this becomes integral over E, and let's use double integral because that's what we use. We take the derivative of the Q part with respect to X minus the derivative of the P part with respect to Y. And we have dx dy. And one of the rules of double integration is that for a nice square region like we have, this splits into an iterated integral, right? So first we will compute, so we can simply compute the derivative with respect to y. That's very simple. So I have 1, 3. And then I will worry about, this one literally splits into two integrals. So what is this? 0 to 2. And you can work this out. This is just 4. It's rather simple. Whereas if you sit and try to parameterize the square, it will take you a little bit of time. So this is definitely one convenient application. All right. Now, another application is to compute areas. So in the first two examples, we were interested in curves. In the third example, we are actually interested in a double integral. And here, what happens is that your del Q by del X minus del P by del Y is being taken as the constant function 1. Okay. So the clever part, sort of the trick in these problems, is what choice of vector field do you want to take? Because there's no unique choice over here. This can turn out to be 1 in several different ways. So this is purely dependent on the problem. Depending on what boundary curve you have, you want to choose your vector field smartly. And again, this is something that I have put in your tutorial as a practice problem. But this is very, very useful. This is often used for computing areas. So I'll sort of not go too deep into this, but I wanted to mention it. But maybe let me mention, let me see the time. Okay, let me mention this another application. So you can also use Green's theorem to prove the transformation law, which is actually one of the most important things about double integration. I'm sorry, my screen is probably doing something weird. Okay. So transformation law for double integrals. What you would call change of variables. So what is this? How does it go? So we'll not give a full proof over here, but maybe if I have some time, I can kind of indicate, where this is coming from. So let's actually write down what the transformation law says. And I'm always working with regions where double integration is well defined. So what I have is I have a region in the UV plane, and I want to transform it into a region, and in the new, I'll call it T. So of course, when I transform, maybe I make this very nice. Okay, so maybe I make this a circle or something like that, if that is possible. Doesn't matter. So you kind of transform it to the shape you desire, if possible, and you have the XY coordinates over here. And how are you doing this transformation? You have to do it in an injective, and at least the function that you use for the transformation should be at least C1 smooth. So that means my new coordinate small x is some function of UV, and my new coordinate small y is some function y of UV. Okay. So what does the transformation law say? So let me call this region S, and that region is already T. So it says the following, that if I want to integrate x comma y dx dy double integral over T, I can transfer this to an integral over S. So the first part is fine. So I'll do f of capital X UV. So now this becomes a function of U and V. But I can't just simply plug in a du, dy, a dv over here. This transformation needs to we need to take something into account over here. And that I will first give you a formal expression. So we write it as del xy divided by del uv. I'll shortly explain what that is. Du, dv. Okay. And what is that? Where del of xy del uv is what? It is a certain determinant. That's why I want this transformation. So my transformation is injective. It is actually surjective onto T, and it is C1 smooth. Okay, and you should have already discussed differentiability of vector valued functions of multivariables. So really C1 in that sense I need. And what is this? You make this Jacobian matrix, which is a matrix of partial derivatives. And you are asking, so there is an additional condition over here. And my additional condition is, let's say for the moment, this is not zero anywhere. Okay. This condition can be weakened a little bit, but I will not talk about that too much. You can let this condition go in sort of insignificant portions of your domain or your region. But for us, we will assume that this is non-zero everywhere. So this is sort of how we distinguish between C1 continuous, C1 smooth curves and regular C1 smooth curves. This non-vanishing of derivative becomes very important in calculus. Okay. So, the logic behind this is really a little bit like easier to explain. And if I have time, I will definitely come back to, how to prove this using Green's theorem. But the idea is really that if you think of du dy, so let's take a little rectangle over here. So think of this as a very, there's a typo in the, let's see, what have I done? I think I have switched my coordinates, right? I think this is what you're referring to. Yeah, of course, these are functions of u and v. So I have to, of course, take derivatives with respect to u and v. Thank you. Yeah. Okay. So remember that at the end of the day, this integration comes by approximating your regions by rectangles. So rectangles play a very important role. And if I take a very small rectangle like this of side del u and del v, so if I look at first this portion over here, this transformation may send it to some sort of curve over here. Okay. Now, and whereas this line may get mapped to some sort of line like this. We don't know, but something like this will happen. Now, if I look at the tangent vectors to these lines, so what is happening to these? So if I look at this transformation, what it's going to do is it's sort of going to send you to a parallelogram at an infinitesimal level. You're going to end up getting, so if I look at the tangent line over here and the tangent line over here, so if I look at now the area of this versus the area of this, then the factor that it gets multiplied by is exactly this. Remember that this is some sort of a cross product over here. And again, when we come to three-dimensional vectors, this will become a little bit more clear. But this Jacobian is really coming from how the areas of small rectangles are getting scaled at an infinitesimal level when you do this transformation. So this area has to, this piece has to account for the change of that area. That is where it's coming from in this transformation law. Okay. Let me pause and see there are questions at this stage.
I have one question. Always we close region will be converted to the closed region, or that can be a line or anything, any not a closed region.
Close? Can you repeat that?
Yeah, in the S domain we are having, S region we are having, there's a closed region we make del U and del V. The corresponding transformation is also closed. So it is always be closed into converted to the close.
Correct. So we do want, so this is always going to be a bounded region. And so you are, I suppose you are thinking of something like this, right? Let's say I want to map this into an open thing like this, maybe. Is this your question? Like, are you thinking of? Yeah. Okay. So the point, actually, technically, there are transformation laws that allow you to do this. The only issue is that sometimes, so of course, if you notice, if you try to do this for constant function 1, then you are actually computing area. The area of this will be finite. And if I draw a bad region here, this area will be infinite, right?
Yeah.
So a priori, it seems that this transformation law is not working. But actually what is happening is that when you can formally apply this transformation law, but when you have a transformation like this, then this term will become very, very large. Okay. So because by the logic I just told you, a very small rectangle is now being forced to go to a very large rectangle, parallelogram. So what happens is this transformation law, there are transformations law for this setting, but then you may not get that the right hand side has integrability, or this region, this capital T region, there your function may not integrate to a finite object. And the problem is coming from the fact that the Jacobian can become very large. That's the problem. Okay, so there are transformation laws where your region, your resulting region does not have to be bounded. It can be sort of this infinite kind of region. That's not a problem. It doesn't have to be like in our picture, but because I was trying to show you transformation law as an application of Green's function, if you want to apply Green's function, I want to stay in the setting of Green's function.
In what condition Jacobian will be 0?
Let's see. So what condition tells us that the Jacobian is 0? So when you say condition, you mean what? Like condition on what? What condition?
No. When we can have the Jacobian is 0 means it is possible any scaling factor is 0.
So you can, okay, so you can have Jacobian 0 even when your map is injective and surjective. So I'll give you a very low level example, right? X cubed.
I think Jacobian can be 0 if x, y are dependent to each other.
Yeah, okay, fine. That's one way of putting it. So you're saying that you mean like x, y are dependent on each other as functions?
Yeah, x can be written in form of y and y can be written in form of x.
So I suppose as functions, you're saying that y is equal to lambda x, like this. Yeah, so this is a very strong condition under which you're Jacobian. So here, so all you need, so for the Jacobian to vanish at even one point, For that to happen, you're really just saying that delta yu comma delta yv at that point P is equal to lambda of delta x of this vector. So what the condition that you are giving me, that y is lambda times x, that is like extremely strong. But this condition just at this point, so Jacobian vanishing is just telling us about this specific vector being lambda times this specific vector. That is what it means. But for that, you have to compute in some sense. I mean, so for example, like I said, like even if your function is injective, like x cube does have a vanishing derivative at the origin, in spite of being injective over there. So just because the transformation can be inverted, you cannot prevent the Jacobian from vanishing. Yeah, so I don't know what kind of condition you're seeking, but in some sense, you almost do have to compute to know your Jacobian over there. I mean, of course, if like, these things like capital F is a point of minima or maxima, but then in that case, you will not get an injective map.
Yes, ma'am.
Right? So if you're a point of minima or maxima, then injective surjective is not there. But I'm saying that even with injective surjective, there is a further possibility of Jacobian vanishing.
Yes, yes.
It's yeah, it's you have to sort of compute. I cannot think of any geometric conditions, but yeah, I don't know if you had something specific in mind. Maybe you can ask.
No, just I'm asking in general, any particular things where this can be zero. I'm asking in general.
Yeah, absolutely. There are like this example, x cube, y cube, and you could modify this and make it a pair also, x cube comma y cube, something like this. Then you'll have invertibility, but when you try to compute its Jacobian at 0, 0, you will get a complete zero Jacobian at that single point. So this can happen, and in terms of the picture, this rectangle is degenerating either to some sort of curve or it's degenerating to a point. That's what's happening geometrically. Yeah.
Okay, thank you.
Other questions? Okay, so given the time that we have, let me go back to Green's theorem and talk about the sketch of the proof. How does this go? And again, let's come back to what regions we are discussing.
Before you go to the proof, I have the reverse. We are applying Green theorem from the left to right.
Okay.
Left right means as for the equation is convert. Single integration is we are to calculate the single integration. Let's say we are using the double integration.
Yeah, we are using exactly. So the way the proof will go is that I will convert this side to a, okay, since you have brought this up, I will convert this side to a integration over BT. I will convert this side to an integration over BS by Green's theorem. And then how do I make these two match? Here I will use the one-dimensional change of variable formula. That's the idea. You're right. So we are going from area integral to line integral for this application.
So what are the application when we require the right to left? Means if we are having the double integration and we are not able to solve something, we can use the Green theorem and we can solve the left hand side. Which condition, which type of problem?
Yeah, so this is one, and like I said, computing areas, right? A lot of times you want to compute an area, that is a double integration. Sometimes it's easier to transfer that. I mean, there are lots of situations where the double integral. Okay, so what can happen? The reason why this can become important is if you look at these differentials dx and dy, then sometimes so dx vanishes along vertical lines. So somehow if your boundary has a lot of vertical lines, then there is some advantage in converting it into a line integral because an entire piece of the line integral drops out on those lines. So geometrically, that might be a motivation to convert to a line integral. Like you have a lot of pieces like this, and if you have horizontal pieces, then dy drops out. But then of course, there could be some other bad pieces. And what happens is then the double integral maybe is a little harder to compute. Remember, for double integral, if you have a region like this, I mean, what is really the method? You kind of have to break it up into rectangle. I mean, you may not have a technique of doing this. That's the problem. Whereas with curves, you can try to parameterize them and get this integral. right? We at least have a way of converting it into a one variable integration. But double integration, I mean, what methods do we really have? Unless your region is already a nice sort of triangle.
Irregular shape you are talking about.
Irregular. Yeah, irregular shape. Exactly. Otherwise, I mean, if you're already a nice shape, then maybe both the integrals are equally, easy or equally hard. Yeah, irregular shapes.
Okay, thank you.
By the way, this is just nothing to sort of, get us too intimidated, but since I work in complex analysis, and if you guys have ever come across any complex analysis, you would have come across the Cauchy integral formula. That's like the main thing on which one variable complex analysis is built. So I don't want to go on and on about it, but since somebody asked me this question, what does that really, that result says that if you have something which is analytic in a region, then you can obtain its value in the interior by integrating that function, whatever this integral means, along the boundary of this domain. And there is a 1 over 2 pi r. So this is just a side remark. If you don't understand what is going on, it's totally okay, but this is known as Cauchy integral formula. It's really wonderful because you can actually compute the value of the function on the inside by simply knowing what its values on the boundary are. And one of the ways of proving this, a very old way of proving this, is by using Green's theorem. So Green's theorem is actually very, very useful even in a lot of theoretical mathematics for obtaining nice formulas like this. I have seen it used a lot of times for these kind of integral. These are known as integral representation formulas. Okay, this is just a side remark. So Shobhan, since I started a little late, can I take some time to just do a sketch of the?
Yes, sure. Yeah, sure.
Yeah, I'll just do a short sketch.
Yeah.
I have a feeling that people would have seen it, but still it's worth going through.
Sure.
All right. So okay. So let me do a sketch of the proof. The main ideas. In any case, this is not really something original that I have come up with. It's available in many nice. So sketch of the proof of theorem 2. And I'll currently do it purely in terms of pictures, and then in the end, we will do a little bit of an argument. Okay, so our picture looks something like this, that we have some shape like this. We are removing some holes from it, and then we have some orientation, which we have set the convention for the orientation. Okay. So the first thing we are going to do is, we don't like the fact that there are so many boundary components. We are going to break up this region into pieces where each piece has only a single boundary component. So for example, I could make a cut like this, and I'll quickly explain what that cut means. And then I'll make a second cut like this over here. Then what do? Then I make a cut over here, and maybe I make a cut over here. Okay. So when I make a cut, there aren't actually two lines over there. It's a single line, and I'm sort of cutting along that line. Okay. I'm just taking my scissors and cutting along that line. So the three pieces that I get, of course, my drawing will not be exact, but they're roughly going to look like this. So I have this shape over here. Then I have something like this over here. Again, excuse my actual drawing. And then I have something like this. Okay, so now each of these pieces, E1, E2, E3, they only have a single boundary each. Okay, so there, if you do the double integral over the full region, you're really just taking the union. This is one of the rules of double integration, that if the overlap is just a line, then the regions, the integrals add up. So they do overlap, but they only overlap along a line, and a line does not contribute to a double integral. But what is happening at the level of curves? So when I have these curves that I am breaking this region up into, then what is happening at the cut? When I try to give each piece an orientation, so if I go along this, I will have to give this an arrow like this, and then I go like this, and I go like this. But now if I try to give the other side an arrow, so let me take a pink line over here. If I take this piece and I try to give this the correct orientation. So what does that have to be? That has to be counterclockwise. It is already counterclockwise over here. But when I come to this part, I get an opposite arrow like this. So these two opposite arrows, they are not going to, in the end, contribute anything because they're going to cancel each other out. So these cuts, when I make these cuts, the integral along these cuts, when considered as part of the two different pieces, they cancel each other out. So there is cancellation here along this cut. So at the end of the day, what's happening is that even the boundary integrals are splitting up as the sum of these three integrals. But here we have to be a little bit more careful because here there is actual cancellation happening due to the orientation. And that is why it is important that we are integrating a vector field along a curve because their orientation matters. If we were just integrating a scalar function, then the orientation would not matter. Okay, so that's the first reason why we can deal with holes is because we can get rid of the holes and only treat these individual pieces then. Okay, so then what happens with each individual piece? So this is the first step. This is the first reduction. The second reduction is to sort of do the following. So this is a two sort of step procedure. So let me for the moment just take something like a bean or something like that. Doesn't matter. Okay, or maybe let me take a shape that we already have. So I don't want to sort of expand on this point too much, but the idea is that we are going to start looking at regions of the following type. So let me call it a special region. And the special region looks like this. It is all those points in R2 such that X lies between A and B and Y lies between the graph of two continuous, this is f of X and this is g of X, where f and g are continuous functions on the closed interval AB. Okay. So what I'm speaking about, over here is it could look something like this. So this is the graph of F, this is the graph of G, and somewhere this is the axis, and I have AB over here. So this is a special region. And here's something I want you to think about, that this guy, my claim is this can be decomposed into finitely many special regions. That's the idea over here. Okay, and so how do we do this decomposition? We just start with saying, okay, where does this start not becoming a graph? So maybe I want to draw a line over here. So, okay, so far it's fine. Then let's see. So in fact, I can go probably I can go, sorry, bad color. So I can sort of draw this region over here. So you have to be a little bit more careful, but maybe if I do this and break it up, then I can see these things as, yeah, so I get some sort of decomposition like this. And I can then get each of these to be this special region. Okay, so, right, I think this is fine currently the way it is, yeah. Yeah, okay, so I'm not going to go too much into that, but you can sit and think about how you can decompose any shape that you have drawn like this into these special regions, again, finitely many special regions. And then there is a different side to this story. I, of course, gave you these regions where the upper and lower side are graphs over X. You could also have the opposite situation where Y lies between A and B, and the left and the right-hand side of the region are graphs over Y. But a similar story will work over here, over there. So the third step is to say something about these special regions. So let E be a special region. And let me call this special region star. For this region, we show, for E, we show only half of the Green's function. So what we will show is the following piece, that if I look at P dx on the boundary of E, I get del P, del Y, del X, del Y over capital P. So what's the idea? Once I'm able to show this, and this actually doesn't take that much time, so I'll quickly talk about this and we can finish. Or maybe, okay, so I don't know, I'm a little worried about going too over time. Okay, so let me just say this a little bit. So you might be a little concerned that what we have done is we have decomposed our region into regions of this special type. So I'll only be able to show half of my Green's theorem. But then I also said that you can do the opposite thing, which is you can also look at the second type of special region in which we are doing something like this. So we are now dealing with shapes of this kind. So here, now you are a function of y. So for these pieces, you will show the second piece of Green's. So here you'll get del q by del x dx dy. And so then you will apply, now you will break up your region into these kind of special pieces, and then you will apply the fact that for each special piece you have this formula, and that will give you the global formula for the domain. So together, when you add these two up, you will end up getting the Green's theorem. So if you think about the proof, we are actually proving each formula separately and then simply adding them up. So we are simply saying that these formulas are separately applicable to our domain, and then we are adding them up to get our final Green's function. And because it's time, I will sort of not really prove this by hand, but since this came up earlier, why is this integral suited for this special region? Because if you notice, there are these vertical lines, and dx will vanish on this vertical lines. So at the end of the day, I will only need to care about the line integral along this curve over here and this curve over here. And that makes things very simple, at least on the left-hand side. And on the right-hand side, what makes things simple is that even though we typically do not know how to integrate over these complicated regions, here we have a straightforward formula. We can do this iterated integral over here. So we first integrate with respect to dy and then integrate with respect to x. That is what makes our life. So that's the advantage of having this simple region. That's what makes the right-hand side easy to deal with. Okay. So I think this is enough for you to try and fill up the gaps. As I said, next time we will start talking about surfaces. So we'll spend more time in 3 dimensions. So we'll also talk about curl and div and things like that. But I think I'll stop over here since you probably have a tutorial after this. And yeah, so Shobhan, please go ahead. If I don't know if there are questions or something.
Yeah, okay. I think we'll
I don't think I can hear you actually.
So Shobhan, you're not audible.
Oh.
Did you see?
Okay, it's not just me then.
No. I also.
hello.
Now we can hear you. You are not audible.
Okay. I just said we will take a quick break, and I think we'll meet at 7:15 for the tutorial. Yeah. I have also created the breakout room, so you could join according to the previous assignment.